IBM Research released FabricX, a new edition of the private DLT built for digital assets and tokenization. By the end of this video, you will know how FabricX differs from Hyperledger Fabric and how to build on it. We have created a live prototype to show you how it works in action. A quick disclaimer here. We assume that you have at least a basic understanding of Hyperledger Fabric. If you don't, watch our previous video on how it works and then come back here. So how is FabricX different from the Hyperledger Fabric? You already know. While it carries the same name, at Espeo software we see it more as a redesign than a point release. IBM Research rebuilt it around 4 core ideas. Consensus first, a new token model, greater privacy, and a new programming model. Hyperledger Fabric already has a Byzantine fault-tolerant ordering service called Smart BFT since version 3.0. FabricX, however, goes a step further by adding a new ordering service called ARMA. A classic BFT orderer runs through the consensus path in full on the leadership node, which limits bandwidth and disk space. ARMA shards the receiving, batching, and storing of transactions across separate machines and lets the consensus order only compact metadata about those batches. This way, you can scale horizontally by simply adding more machines. By IBM's own benchmarks, ARMA runs at roughly 10 times the throughput of standard ordering service, up to 20,000 transactions per second. And when built as a standalone system, IBM reported peaks past 200,000 transactions. That kind of horizontal scaling is what sets ARMA apart from a standard orderer. The second idea is the token model. In Hyperledger Fabric, the ledger is essentially a database of balances. To move tokens, you update a record. FabricX uses a UTXO model instead, meaning that each token acts as an independent output. This is the same model that Bitcoin uses. Because each output is independent, transactions can run in parallel instead of queuing behind the same record. That is part of where the throughput comes from. Tokenization is no longer something you simulate on a database. Here, it is the native unit. The third idea is privacy. Classic Hyperledger Fabric obviously does not ignore privacy. It has private data collections to wall of data and an anonymous identity stack called Idemix for anonymous credentials. FabricX simply gives you a different kind of privacy because zero-knowledge proofs are built into how tokens work. Balances and amounts stay hidden by default and can still be proven correct without being revealed. Two parties can transact on the same ledger and never see each other's balances. For a private permissioned ledger, that changes what you can keep confidential. And the fourth idea is the programming model. This is the one your engineers will feel the most. In Hyperledger Fabric, business logic lives in a chain code deployed on a network. In FabricX, IBM moved it into the Fabric Smart Client views. These are classic Golang functions which enable participants to negotiate a transaction peer-to-peer, agree on it, and only then commit it to the ledger. It is more flexible, but it is something new and unfamiliar. We'll come back to that when we talk about the learning curve. Let's zoom out a bit. Classic Hyperledger Fabric is sometimes called a shared database with smart contracts on top. FabricX is a tokenization engine, UTXO tokens, private by design, negotiated peer-to-peer, and ordered by a consensus built to scale out. Once you decide to build on FabricX, there is a second decision you need to make, and that is how to actually do it. IBM gives you two paths. The first is the native token SDK. This is the path FabricX was built for. You work in Go through the Fabric Smart Client views. The SDK already provides the core token operations, issuing, transferring, redeeming. You define your token and your participants, say an issuer and two investors, and adapt those operations to your rules. UTXO tokens, peer-to-peer protocols, and zero-knowledge privacy come built in. In our prototype, one investor could not see the other's balance. That masking is enforced at the protocol level. The second is EVM path. It puts an Ethereum virtual machine on top of FabricX, and here you don't need to learn anything new. You write a Solidity smart contract, a standard ERC20 token, or a restricted one like ERC1404, and deploy it with the tools you already use, Hardhat and MetaMask. ERC1404 adds transfer rules on top of ERC20. You keep a whitelist and only approved accounts can hold or receive the token. In our prototype, a transfer to a non-whitelisted account was rejected, with a readable reason for why. The difference that matters most is privacy. On the native token SDK, it is built in, as you just saw. On the EVM path, it is not. You can still achieve it, but you have to build it yourself in the contract or application code. And privacy is much harder to add later than at the start. This is the kind of stack decisions our digital assets team at Espeo Software helps banks and fintechs walk through. If you are waging it right now, reach out to us via our forum. So the trade is simple. The native token SDK gives you privacy and advanced tokenization out of the box. The cost is an unfamiliar programming model. The EVM path gives you familiar tooling and Ethereum compatibility. The cost is building privacy yourself. Specifications are a promise. The only way to truly know how a platform will work is to build it. That is why we build a prototype for both of these paths. Continue watching to see what we found. Starting with the good news, on the EVM path, transactions were advertised at around 2200 milliseconds. In our prototype, we got that down to roughly 580, far faster than advertised. The problem is that when a transaction was blocked, that event was not written to the chain. For an auditor, the record of what was refused is exactly what they need to see. We also hit an undocumented bug. When we queried the event history through the standard Ethereum call, it returned an empty array. We have reported it as an issue 192 on the FabricX EVM repository, but it has not been fixed at the time of writing. The native token SDK sample does not have a separate auditor node either. The role exists in the SDK underneath, but you have to build that piece yourself. There isn't a block explorer for the token SDK path at the time of writing, but the EVM path does. These are very young, but we thought it would be valuable to highlight, and we look forward to creating a follow-up once these changes are implemented. So, to summarize, if you need to be compatible with Ethereum and Solidity and you have a team that knows the ecosystem, take the EVM path. If you need whitelisting, we recommend adding a restricted token standard like ERC1404. If you need privacy and advanced tokenization, take the native token SDK path for confidential balances and zero knowledge by default, and accept the steeper learning curve. With our prototype, we confirmed that the foundation works, but you still need the right legal structure around the assets, secondary market trading, and reporting. If you need help building these, contact us and we will be glad to support you. So, is FabricX ready to carry a production platform now? We think it's getting there, but there are still quite a few open issues that need fixing. We see this as a strong signal for where tokenization is heading, especially when it comes to enterprise infrastructure. We spent this video on the settlement layer. The Rails tokenized assets move on, but the Rails are only half the story. The institutions moving fastest are not only rebuilding how to settle value, they are building something on top of it, their own internal AI operating systems wired into the same infrastructure. In the next video, we look at what those systems actually look like inside a bank and why the people building them are so important for these businesses. Please consider subscribing, and as always, remember to stay on the block to stay ahead.